G'day viewers. I recently saw a question on a Facebook page about generators being in kVA and kilowatts. And there was a couple of hundred comments on it where people arguing, saying generators are not in kilowatts, and yet others were saying, well, they've got generators at their work site and that they are in kilowatts. Others saying, no, they're only kVA. So I thought I'd clear this up a little bit. Generators will generate an EMF for us. So let's say we've got an EMF or a voltage. Okay, there's our voltage sine wave. Now, if it's not hooked up to a circuit, all it gives us is voltage. And when we look at power equals voltage times current in amps. At this point where we've just got voltage, we got no power because it's not hooked up to anything. Now, I won't go through the power triangle. I've already done that. So there's a video that I've done on a power triangle. But what I'll say is that the output or the power that we get from the generator or that we use from the generator depends on the load that we hook it up to. If we were to say what kilowatts will the generator give us, that's a bit like saying if we hook the generator up to lights, how much light is it going to produce? And of course everyone will say, well, it depends on the type of lights you hook up to the generator as to how much light you're going to get. Same with kilowatts. Kilowatts is what you use, not what you generate. So voltage and current is what you generate, but the power in an AC circuit is what you use. So the true power or the kilowatts is actually what you use, what you convert that voltage and current into. So let me show that if we were to hook this up to a resistive load where it'll allow the current and the voltage to go through the circuit at the same time, then we're going to get a current sine wave similar to that. It's going to start at the same time as the voltage. And of course we've got voltage, we've got current. Voltage times current will give us power. All right. However, if we hook this generator up to a load that is not going to allow the voltage and current to travel in sync. Now, what would cause that? Certainly one of the biggest workhorses we got in industry, inductors. So windings, anything with windings in it. And of course, let's say a motor. We hook this up to a motor. We know that that motor needs to develop a magnetic field. It gets that magnetic field from the current, not the voltage. So the motor is going to allow the voltage to go through the circuit, but the current, it wants to use that current to build that magnetic field in the windings. And that takes time. For us, it looks like it's instant. For an electrical circuit, it's not instant. It's quite slow. So what happens with our sine wave is that the voltage will be allowed to go through the circuit, but the current is held back for a time until the flux is built in the motor, and then it allows the current to go through the rest of the system. So the inductance in the motor is acting as opposition to current, and that's exactly what it is. So inductance is opposition to current flow. So that time period that it's opposing the current flow, there's only voltage. So let's say our current now starts off here. Okay, so before, when the current started off at the same time as the voltage, we had voltage and current, which gave us power. Now, because we've got this time period here where there's no current, we've just got voltage, then we've got no power. at that time. We don't have any power until the current starts, and so then we've got current times voltage gives us power. But that power is only going to be there for that time period that they're both on the same side of that line. And so then we're going to lose our power again until they're both on this side of the line. And we're going to have power only up until the voltage again disappears to the other side. So you see these gaps here. That's where we've got no power. The generator is still giving us voltage and current, but we're not using it. Not to actually turn the motor. We're using it to build that flux. So now this is where the kilowatts comes into. So it's not giving us the full voltage times current. Like I say, the generator is still giving us voltage and current, but that voltage and current is not being used. Let's say we've got a 200 kVA generator. But because of these gaps here, we're not actually converting all of that voltage and current into usable power. So we might only be converting that into 160 kilowatts. Now, some generator manufacturers could well call this a 160 kilowatt generator because they've already taken into account that most likely you're going to hook it up into a load that's going to have these 20% losses in it. So it could be a 200 kVA generator, but they call it a 160 kilowatts. Now, of course, if you hook this up to a load that is going to have even more losses, let's say it's 50% losses, that would be, if you look at the power triangle video I did, then that would mean a 0.5 power factor. If we've got a 0.5 power factor, it's not even going to give us 160 kilowatts. It'll only give us 100 kilowatts. But that's what they figure is the norm, that you probably have 20% losses in your circuit, and so it'll be 160 kilowatts. Now, transformers will never be in kilowatts. I would think the reason for that is that a transformer is definitely going to be purchased by an engineer or an experienced electrician that understands power factor and what they can get out of it, whereas a generator could be ordered and installed by anyone. And so it could be that that's the reason why some generator manufacturers will give it a kilowatt rating rather than a kVA. Well, I hope that helps. If there's any questions, please put it in the comments below, and I will do some more videos on that subject if I didn't explain it adequately enough. So that's my take on it. Hope it helps.